Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are going to have a hands-on session on assessment of compound climate extremes. So far we have understood the criterion to establish cold waves, their drivers and impacts. We also appraised the concept of compound climate extremes and the ways to estimate them, and we lastly deliberated on heat wave and cold wave mitigation strategies. What are the learning objectives for today? First, we'll analyze daily temperature and rainfall data. Then we'll establish percentile-based thresholds to identify compound extreme events. Then we'll also use the monthly data. So from daily data, we'll derive the monthly data. Using that, we'll derive standardized precipitation and temperature indices, and that will be used to establish SPI and STI based thresholds to identify again climate extremes, compound climate extremes. So quick recap. So compound climate extremes are simultaneous or sequential occurrences of multiple climate hazards such as heat waves with droughts or flooding with high winds that interact to produce more severe high impact disaster than an individual event. These are usually driven by global warming and internal climate variability, and these pose a significant threat to ecosystems, infrastructure and human health. So looking at the categories, so there are four types of compound extreme: hot, wet, example is flood and heat stress. Next is hot, dry, which is drought and heat wave. Cold, wet, which is extreme rainfall and snow. And last is cold, dry, which is also known as a cold drought or snow drought. So in this hands-on session, we are going to mainly focus on two approaches. One approach is based on SPI and STI based thresholds, and second approach is based on the percentile based threshold. So the input data which we are taking, so we have used the gridded rainfall data from IMD at 0.25 degree resolution, and maximum and minimum temperature data for the period of 2001 till 2023, and that is in XLS format. So if you can see the data format, you will have year, month, day, T max, T min, T average as well as rainfall. So these are all values at a daily time scale for one particular grid, and that you can extend it to any number of grids. So we are just demonstrating the process for a particular grid. So coming to the first approach, where we discussed SPI and STI based threshold. So we have already seen while we are discussing droughts that SPI is a widely used indicator to measure precipitation anomalies relative to long-term climatic conditions. So based on the SPI values, we can classify dry and wet scenarios at different locations. So for our analysis, we are going to use SPI 1, so at one time scale. So SPI is P minus mu by sigma, so where mu is a mean precipitation and sigma is a standard deviation. So this has to be done on a monthly scale. So for each month, you will have to take the mean and standard deviation to compute SPI. Here we are taking a threshold of plus or minus 1. So SPI 1 values greater than equal to 1 will be taken as wet, and less than equal to minus 1 will be taken as a dry scenario. Analogous to that, we have STI, which is standardized temperature index. Again, it will quantify the temperature anomalies relative to long-term mean temperature. So this will help us identify the cold extremes. So for this, we are taking T average time series, that is the average temperature, and based on that we classify using again the threshold plus or minus 1 into hot and cold climates. Now how will we identify compound extremes? So in this hands-on exercise, we'll use SPI and STI in a combined manner to get this classification. So if SPI is greater than 1 and STI greater than 1, it is hot, wet. If SPI is greater than 1, STI is less than 1, it becomes cold, wet. SPI less than minus 1 and STI greater than 1, it is hot and dry. And if both are less than minus 1, it becomes cold and dry. So what steps we'll be doing? First, we'll convert your daily data into monthly data. Then we'll calculate SPI 1. Then we'll calculate STI 1. We'll identify the compound events. Then we'll plot SPI 1 versus STI 1, and then we can also count the number of hot dry days, and similarly other categories of events. And lastly, we'll see by plotting them so that what are the temporal variations in that particular extreme. So here's a MATLAB code. I'll quickly go through the MATLAB code. So we are inputting the Excel file. So this is the Excel file which will be there, and we are defining the variable like year, month, rainfall and average temperature. Mind you, here we are considering average temperature, not minimum and maximum temperature. Now next set of commands which we are using, that is used to convert your daily data into monthly data. So for rainfall we are doing totals, so we are summing up all the data in a particular month, and for temperature we are taking the average of all average temperature values in that particular month. Once it is done that, then we'll go for SPI and STI based estimation, so that we have already seen. So here we are estimating the standardized index, that is R minus mean divided by standard deviation for SPI, and T minus T mean divided by standard deviation of T, that is for STI. Mind you, we have to do it on a monthly time scale. For each month we have to do separately, that is month wise standardization. That is why this for loop is from 1 till 12. Once you have identified this SPI and STI, then the next step is you will do the compound extreme classification. That is, we already discussed the threshold is plus and minus 1. Based on that you have 4 categories, and if the events are not falling in any of these, that is if the events are between plus and minus 1, so that they are normal conditions which will not be counting. We are only counting the extreme condition. Then this array function command, so this is giving us sum, so this will count all the number of extreme events into all these 4 categories, and finally in a tabular manner we'll be able to display them and finally export to a XLS file. And lastly we create a figure out of it, that is a stacked bar chart where we will see for each year how many number of compound extremes occurred at that particular grid. So with this, let us run this code through MATLAB and understand the changes. So I am shifting to the MATLAB online. So I have already loaded my files. This is my Excel file, that is hands-on_compound extreme, and there are 2 MATLAB codes for approach 1 and approach 2. So for approach 1 this is the code. Let us see how our Excel file looks like. So this is the Excel file which is imported here. So we'll be taking 2 columns, that is T average as well as rainfall. So let us quickly run through the code step by step to understand how it is happening. So we are running selection. So now we have input the data, so you can see our data file. It is 8400 into 7. So this is my data file. So for 23 years I have 8400 entries. Now I'll convert my data into monthly. So I'm running this part of the code. So if you can see R and T, so now I have 276 values, that is 23 into 12. So this is my monthly rainfall, and next I get is the monthly average temperature. So this is how I am converting my daily to monthly values. Next I'll go for the standardization. So I'll run the third section and let us evaluate the standardized values. So my standardized values SPI 1. So you can see my values SPI 1 for each month as well as my STI 1. So these values are documented here. So you can see several values are less than -1 here, and when we talk about rainfall, the values are showing +2. But what we need to do, we need to find the intersection between those values, so they are occurring at the same time. So these kind of extremes are called concurrent extremes. We are not taking the temporal compounding events. Temporal compounding events will have certain lag. We are taking concurrent events. So both SPI 1 greater than 1 or STI 1 greater than 1 should occur at the same time step. That is what we want to find it out. So for instance, here you can see at time step 6 it is -1.59, and time step 6 here it is +1.2. So SPI greater than 1 becomes your wet, and STI less than -1 becomes your cold. So it is a wet and cool type of extreme that is being located here. Then we'll do the event classification as discussed. So we are running this particular section. So you can see you have another matrix of event. So you can see as discussed that at point number 6 you get a cold wet event. So that is what we inferred from the SPI and STI cycle. All other events which are not extreme fall under normal category. You can see here it is a hot wet event and so on. Now what you will do, you will just count all these 4 categories of events which are hot wet, cold wet, hot dry and cold dry, and it gives us a table. So if we see this particular table, So it will give you in each year how many number of hot wet, hot dry, cold wet and cold dry events have happened. So you can see more or less they are balanced, not much, but you can see on an average cold wet events are more predominant as compared to other events. So to get a more better overview, let us plot these results. Once we plot it, we will be able to visualize them much better. So you can see these are the legends which we have shown here, and you can see 2001 had the highest count, that is 3, and then other years had 2, and some years did not show any compound extreme events. But you can see cold wet is the major category, hot wet is at one location, and hot dry you can see at several locations. So this is how, using the first approach, we were able to identify the occurrences of all 4 compound typologies. So cold dry events were not seen at all at the grid which we have analyzed. Now going back to the presentation, we will check the results. So these are the same results which are showing here. Now let us go to approach 2. Approach 2 is the percentile based approach. In this approach, unlike your SPI and STI, we are using 25th percentile and 75th percentile based on the daily data. So although we are using daily data, we'll compute month-wise percentiles. Why we are computing month-wise percentiles? Because the climatology of January month will be totally different from the June month. So if you take an overall percentile, we can make lot of errors in estimating the values. So month-wise specific percentile, if the values are exceeding or falling beyond this threshold, then we account that. For example, January values are only compared with the January threshold, so that will account the seasonal variability. So what are the steps to be followed? We will consider that so just one correction, we are not converting the data from daily to monthly. We are using the daily data. We are just computing the percentiles which are month-wise. Okay, so we are just using the daily data. Then January value is compared with the 75th and 25th percentile of all January months. So using all January months, that is 23 January months you have, then based on that you compute the 75th and 25th percentile value for the variables Tmax, Tmin and your rainfall. Now to classify cold events, we are using minimum temperature, and classify hot events, we are using the maximum temperature. So if it is greater than 75 percentile of Tmax, it is hot, and less than 25% of Tmin, it is cold. And rainfall greater than 75 percentile is wet, and less than 25 percentile is dry. And then we'll detect the compound events and their year-wise estimation, and finally the plotting. So these are the steps to be followed. Coming to the MATLAB code as discussed earlier, so here we are using 3 variables, that is rainfall, Tmax and Tmin. Here we are grouping them into monthly. We are not converting into monthly. In other case, we were converting them by taking totals. So we are applying a split apply command where we are grouping them. So here we are grouping them into monthly so that we are able to segregate that. And then we are establishing month-wise percentile thresholds, and the thresholds are computed here for each particular month, and then we are applying this particular criteria to classify the compound events, and rest of them which are not extreme remains the normal event. And then we do counting, that is same as the previous approach, and finally a stack bar chart. So overall the code remains same for these particular aspects. So let us run the code and see the second part of the code. So I am going to the second part. So let me clear the earlier variables so that there is no overlap. So let us run code step by step. So first let us load the data. So data remains same. We have additional field, that is Tmax and Tmin. Now let us group the data into monthly values. So you have all these data. Then we will calculate the month-wise percentile thresholds. Moving ahead, we will discuss the percentile based approach. So as I discussed earlier in my theory lecture, so for percentile based approach there are two things: either you can work with daily data or you can work even with monthly data. So researchers have used both the approaches. So we are going to follow a monthly approach. So in this case, again the series which we use, that is we use the daily data and convert it into monthly data, we are using the same, but instead of STI and SPI, we are using the 75th and 25th percentile for each month. So month-wise percentiles will be calculated. For example, January values are compared with only January thresholds. So that will account the seasonal variability. So the steps are, we'll convert daily values to monthly values, we'll calculate the percentiles of month-wise, that is for January. We are pulling up all January months. So we are having 23 years of data. So we'll pool all 23 years of data to calculate 75th and 25th percentile values for the January month, and so on. For rainfall, if the rainfall values are greater than 75th percentile, we classify it as wet. Rainfall less than 25th percentile is dry. For hot conditions, we are using Tmax, which is greater than 75th percentile is hot, and for cold we are using Tmin. If it is less than 25th percentile, it is cold. Then we detect the year-wise compound events and then we plot them. So looking at the code, so first part of the code is where we will read the data, and here we are using additional variables, that is Tmax and Tmin in addition to rainfall. Then we are converting daily into monthly data, that we already did in the last code as well. Now we are establishing month-wise thresholds. So this threshold, so we are initializing the variables and then we'll estimate the month-wise threshold. So this is what the for loop 1 to 12. So we are estimating the month-wise thresholds, and then event classification as discussed, and which are not extreme will come under the normal category. And then we move on, we will use the array function to just compute the count of each events under all these 4 categories, and then we prepare a stacked bar chart to compute these kind of to visually represent these events. So let us run the MATLAB code and we will see in more detail. So we'll run it step by step. So I'm running the selection. So now I have the data 8400 by 7. So I have Tmax, Tmin and rainfall. Now next is I will be converting from daily to monthly values. So we have 276 by 1 matrix. Now let us estimate the month-wise thresholds. So this threshold estimation will run the selection. So let us see R75. So we are getting these thresholds. So you can see for each month, that is January, the threshold is 32, again January the threshold is 32. So we are just rather than creating one matrix, we are creating all, so that it will be very easy for comparison. Otherwise you have to go into several for loops. So to avoid the for loops, we are using same size of the matrix, that is 276 by 1, where the first 12 values are repeating constantly. Similarly, you can have the 25th percentile threshold. So you can see these values are lower. In certain months where there is no rainfall, the threshold is 0. Then Tx75, that is 75th percentile threshold of maximum temperature. You can see in the months of April, May and June, the thresholds are crossing 40 degrees as well. And Tn25, where we can see in months of January and December, the thresholds are going below 10 degrees as well. So they are visibly cold wave conditions are there. So once you have done this month-wise threshold, then we do the event classification by simply counting the values. So we have the event matrix here. So you can see the event matrix, you have all the conditions: cold, wet, normal, cold, wet, normal. So then we'll evaluate the next selection. Mind you, since we are using different approaches or even on the same data, you may get different results. So that is why you cannot compare the results from both the approaches, because both have different thresholds and different methodology. One is a standardized based, other is a percentile based. So each one of them has have their different perspectives, and they should be analyzed with in the same reference frame. And finally we'll plot the results. So on plotting results, we can see that we are compared to the previous approach, which is a more conservative approach. This approach gives more number of compound extremes, where we can see cold wet is more predominant. We get all kinds of extreme. We can see cold dry, hot wet, and even hot dry. So certain years are having as more as 6 months of compound extremes are seen in certain years. So these are the results. So you can see the year in particular 2001, 2020 and 2021, and even 2008. These years are having more frequency of compound extremes. So coming to the last part, here's an activity suggestion for you. You can estimate the SPI and STI for a given catchment or meteorological subdivision at each grid point, considering at least 25 to 30 years of data. Then you apply a suitable threshold and convert it into 4 categories of compound events. Then you compute the spatial extent of all event types, that is for hot wet, hot dry, cold wet and cold dry. What is the spatial extent using the formulas which we have discussed in earlier lectures. Then you also compute the frequency change per decade for all compound extreme types. Now this analysis would provide you the understanding of how compound extremes have evolved spatially as well as temporally, and which is the dominant compound extreme typology. So that will be information we'll be getting from this. So thank you for your attention.